Hey guys, welcome to the second tutorial in the AI series. In today's video, we are going to take a look at what exactly is supervised learning and how it actually works. So let's get straight into it. In the previous video, I gave you a one-sentence definition of supervised learning, which is teaching a computer from examples where the answers are already known. That's true, but it's quietly hiding almost everything that is quite interesting. Because learning from labeled examples raises three questions it never bothers to answer. First, what exactly is being learned by a machine learning model? Well, not patterns, but it's something more than that. Second, how is it learned? What physically changes inside the machine as it improves? And third, once it's done, how do we know it worked? Those three questions are what this entire module is built to answer. So let's stop describing supervised learning from the outside and deep dive into it. Question 1. What is the machine actually learning? Picture this somewhere. There exists a perfect rule that maps any house to its true fair price, or any email to whether it's genuinely spam. Call it the true function, the real answer generator behind the data. We never get to see it directly, but if we did, we wouldn't need machine learning at all. What we build instead is an approximation of it, reconstructed only from the examples we happen to have. But here's a decision that secretly shapes everything, and the previous video never actually mentioned it. Before learning even begins, we must choose what kind of approximation we'll allow. A simple straight line relationship on a graph, a gently curved one, a spiraling neural network with billions of connections. That family of allowed functions has a name, the hypothesis class. And every family comes with adjustable knobs called parameters. A straight line has exactly two. A large language model has hundreds of parameters. So, learning the mapping really means something concrete. Pick a family of functions, then hunt for the precise settings that make your approximation line up with the answers you already have. Now, the second question, and this is the one the previous video just went across. And that is, with every mistake the machine learning model makes, it improves. Now, let's look at that more deeply, because it's the engine of the entire model. The machine starts with random settings, so its very first predictions are quite incorrect and honestly garbage. Then we do something simple and relentless. We measure exactly how wrong it is. For every example, we compare the prediction to the true answer in the label, and we boil all that disagreement down into a single number. That number, the total wrongness, is called the loss. And learning, stripped to its mechanism, is just this. Change the settings in whatever direction makes the loss reduce, then measure again, and then change the settings again. Thousands upon thousands of times. The labels are what make this even possible. They're the answer key the machine grades itself against on every single pass. That precisely is why it's called supervised. The supervision is the constant presence of correct answers steering every adjustment. Take the labels away, and the engine has nothing to push against. Exactly how the machine figures out which way to nudge is the whole point of the next video. But the loop itself is predict, measure, and adjust, which is the heartbeat of every single machine learning model. Now, there's a quite expensive mistake in this field of machine learning. Picture the example as points and the model as a curve trying to pass through all of them. Give the model enough corrections and it can twist itself into a curve so flexible it goes through every training point perfectly. The training points refer to our labels, which is our data with examples. Now, if the curved line goes through every single training point perfectly, There is zero loss, a flawless score on your data you have, and the intro celebrated models that keep getting better and better. So, surely perfect is the dream, right, for every single AI model? Now, hold on to that thought for a second, because the answer is going to feel completely backwards. A model that fits in trading examples perfectly is very often a worse model than one that doesn't. Now, why on earth would that be true? Here's why. The goal isn't to be right about houses whose prices we already know. That's pointless because we already have those answers and the AI finally gets them. The whole purpose is to be right about a new house the AI has never seen. And a model that's all confirmed itself to nail every trading point usually did not learn any underlying pattern at all. It just memorized the examples, all the noise, and after that, when you show it fresh data, it absolutely fails. That's the difference between memorizing and understanding. And we measure it honestly. We hide a chunk of labeled data away and forbid the model from ever training on it, and then test it there. That hidden slice is called the test set, and we'll look at it more detailed in a later video. One quiet assumption holds this whole thing together, and it's worth naming out loud. We assume new data comes from the same world as the training data, the same underlying distribution. A fraud detector trained on last year's scams gets blindsided by this year's precisely because that assumption quietly broke. So, the real target of supervised learning isn't a perfect score on the training set, it's generalization, being right about the test set and being right about the future. That is known as fitting. Predicting what you haven't is the entire job. Whereas memorizing is quite easy, but the AI model will always fail when you memorize. So that's the supervised learning with the hood up. Choose a family of functions, change its settings to drive down a loss measured against labels, and then judge it when the data is quite new and is the new test set. Every algorithm in the next several videos lives inside this very loop. And the first very branch in the videos to come is a single deceptively simple question that splits supervised learning cleanly into two. Is the answer you're predicting a number like a price or a category, like spam or not? Those two roads use different maths, different geometry, and even carry different names. And that fork is exactly where we go next. If this video helped you understand how supervised learning works, make sure to subscribe and hit the like button for more videos like this.